Have you ever looked up at the night sky and wondered where it all began? The vastness of space holds countless mysteries, but one question has captivated humanity for centuries. Are we alone in the universe? New evidence suggests that the very ingredients for life on Earth might have come from space, hitching a ride on meteorites billions of years ago. This incredible discovery isn't just rewriting our planet's history, it's revolutionizing our understanding of life itself. Join us as we delve into the fascinating world of astrobiology and explore how these celestial messengers might hold the key to unlocking the secrets of life's origins. For centuries, we've gazed at the stars, searching for answers to life's biggest questions. Where did we come from? How did life begin? Are there others out there like us? Now, thanks to groundbreaking research, we're closer than ever to understanding the cosmic connection to our existence. The idea that life's building blocks came from space might sound like something out of science fiction, but the evidence is compelling. Meteorites, those ancient travelers from the depths of space, have long been known to contain organic molecules, the carbon-based compounds essential for life as we know it. Recent discoveries reveal specific molecules within meteorites, strikingly similar to those found in living organisms on Earth. These molecules, known as nuclear bases, are the fundamental components of DNA and RNA, the genetic blueprints of all life on our planet. While the presence of these molecules in meteorites doesn't definitively prove that life on Earth originated from space, it does lend significant credence to the theory. This concept, known as panspermia, proposes that life could spread from one planet to another, or even from one star system to another, carried by these celestial wanderers. If panspermia is correct, it has profound implications for our understanding of life in the universe. It means that life could be far more common than we previously thought, potentially existing on countless worlds scattered throughout the cosmos. To understand how life's ingredients might have arrived on Earth, we need to rewind the clock about 4.6 billion years, back to the very beginning of our solar system. Imagine a vast, swirling cloud of gas and dust, remnants from the explosive death of a previous star. This cloud, called a nebula, was the chaotic cradle from which our sun and all the planets were born. Within this swirling mass, gravity acted as a sculptor, pulling particles together and setting in motion a chain reaction of cosmic construction. As gravity drew these particles together, they began to collide and stick to each other, forming larger and larger clumps. Over millions of years, this process of accretion transformed the diffuse nebula into a more structured disk. At the center of this disk, the densest region, our sun ignited, bathing the surrounding space with light and heat. Within the protoplanetary disk, amidst the swirling gas and dust, a new generation of objects began to emerge, planetesimals. These small rocky bodies, ranging in size from meters to kilometers, were the building blocks of the solar system's rocky planets, including Mercury, Venus, Earth, and Mars. Formed through the relentless pull of gravity, planetesimals acted as cosmic vacuum cleaners, attracting and accumulating the surrounding dust and gas, steadily growing in size and mass. The early solar system was a chaotic and violent place, with planetesimals constantly colliding with each other. Some collisions were catastrophic, smashing these nascent worlds apart in a shower of debris. Others were more constructive, with planetesimals merging together, their gravity binding them into ever larger objects. Over millions of years, this cosmic dance of destruction and creation sculpted the inner solar system, gradually transforming it from a chaotic cloud of dust and gas into a more ordered collection of planets and moons. Not all planetesimals were destined to become planets. As these planetary embryos continued to evolve, their compositions began to reflect their location within the protoplanetary disk. Those that formed in the inner solar system close to the Sun were primarily composed of rocky materials, as the intense heat and radiation had long since driven away most of the volatile ices. These rocky planets, with their solid surfaces and relatively thin atmospheres, would become the terrestrial planets: Mercury, Venus, Earth, and Mars. Further out, beyond the frost line, where temperatures were frigid, a different kind of planet began to coalesce. Here, in the outer solar system, ices were abundant, providing a vast reservoir of material for planet formation. These icy giants, Jupiter, Saturn, Uranus, and Neptune, grew to enormous sizes, their gravitational pull shaping the outer solar system and influencing the orbits of countless smaller objects. The formation of the solar system was a complex and chaotic process, a cosmic ballet of colliding planetesimals, swirling gas, and gravitational interactions. Now let's fast forward billions of years from the chaotic birth of the solar system to the present day. We've talked about planetesimals, those building blocks of planets, but what role did they play in the emergence of life on Earth? Well, sometimes these ancient remnants of the early solar system pay us a visit, arriving in the form of meteorites. These celestial messengers, often no larger than a pebble, carry within them a record of the conditions that existed billions of years ago, providing valuable clues about the origins of our planet and the ingredients that made life possible. Meteorites come in various types, each telling a different story about the early solar system. Some are fragments of asteroids, those rocky bodies that never quite grew large enough to become planets. Others are pieces of comets, icy wanderers that periodically grace our skies with their spectacular tails. And some, the rarest and most intriguing of all, are thought to be remnants of planets that were shattered in the early solar system's violent collisions. By studying the composition of these meteorites, scientists can piece together a picture of the materials that were present in the early solar system, including the essential ingredients for life. To answer these questions, scientists have turned their attention to a particular element, zinc. Zinc is a trace element, meaning it's found in relatively small amounts, but it plays a vital role in many biological processes. It's essential for the structure and function of proteins, DNA replication, and cell signaling, among other things. Without zinc, life as we know it would be impossible. But zinc is also interesting for another reason. It acts like a fingerprint, revealing the origins of other essential ingredients for life known as volatiles. Volatiles are elements or compounds that have relatively low boiling points, meaning they easily evaporate and become gases at relatively low temperatures. Understanding how volatiles were delivered to Earth is therefore essential for understanding the origin of life. Remember how we talked about the early solar system being a hot and chaotic place? Well, that heat had a significant impact on the planetesimals that were forming. Planetesimals that formed close to the Sun in the inner solar system were subjected to intense heat and radiation from the young Sun. This caused many of them to melt, a process known as differentiation. During differentiation, heavier elements like iron and nickel sank towards the center, forming a core, while lighter elements, including volatiles, rose to the surface and escaped into space. These melted planetesimals, which gave rise to planets like Mercury, Venus, and Mars, lost a significant portion of their volatiles in this process. However, not all planetesimals suffered this fate. Those that formed further out in the solar system beyond the reach of the Sun's intense heat were spared from melting. To uncover the origins of Earth's volatiles, researchers at Cambridge and Imperial College London embarked on a meticulous investigation focusing on the element zinc. Zinc is not just any trace element, it provides a unique isotopic signature that allows scientists to track its journey from the solar system's formation to its present-day presence on Earth. By studying zinc in meteorites, the team aimed to understand better where Earth's volatiles came from and how they were delivered to our planet. The research began with collecting a diverse array of meteorite samples, each originating from different types of planetesimals. These samples were then subjected to a rigorous isotopic analysis to measure the specific ratios of zinc isotopes. This process involved precise mass spectrometry techniques capable of distinguishing between the subtle differences in isotopic compositions, allowing the team to trace the origins of the zinc found in these meteorites. By comparing the isotopic profiles of zinc in meteorites to those found on Earth, the researchers could determine how much of Earth's zinc came from different parts of the solar system. The team's analysis revealed that Earth's zinc has a dual origin, with approximately half coming from the inner solar system and the other half from much further afield, beyond the orbit of Jupiter. This discovery was pivotal in understanding the diverse sources of volatiles that contributed to Earth's formation. The inner solar system, being closer to the Sun, was a region where planetesimals were more likely to melt due to intense solar radiation. Consequently, these bodies lost a significant portion of their volatiles. On the other hand, the outer solar system was a much cooler environment. Here, planetesimals formed with a higher content of ices and other volatiles, as they were less affected by the Sun's heat. These unmelted planetesimals retained their original volatile-rich composition, making them crucial carriers of these essential elements to the inner planets, including Earth. One of the most significant findings from the study was the crucial role played by unmelted planetesimals. These bodies, which formed further from the Sun and avoided the intense heat that caused melting, retained a much higher proportion of their original volatiles. The isotopic analysis showed that while melted planetesimals contributed to around 70% of Earth's mass, they only accounted for about 10% of its zinc content. This stark contrast indicates that unmelted planetesimals were the primary carriers of volatiles to Earth. These bodies, rich in zinc and other essential elements, bombarded the early Earth, delivering the materials necessary for forming its oceans and atmosphere. This influx of volatiles was a critical factor in making Earth habitable, providing the environment needed for life to emerge. The preservation of volatiles in unmelted planetesimals also offers insights into the conditions of the early solar system. Research on zinc tracking reveals Earth's volatiles, including water, came from unmelted planetesimals. This challenges the view that volatiles were sourced from the inner solar system. Understanding volatile delivery helps answer how life began on Earth. Water and essential volatiles are crucial for life to arise. This research clarifies how these materials were acquired, aiding the emergence of life. These findings also impact the search for life beyond Earth. Scientists can refine models for exoplanet habitability, increasing the likelihood of finding life. Unmelted planetesimals delivered volatiles to Earth, crucial for life's emergence. Volatiles, especially water, were fundamental in creating life-supporting conditions. Imagine early Earth bombarded by volatile-rich meteorites. Each impact brought water, carbon dioxide, methane, transforming Earth's surface. Volatiles interacted with rocks, creating a dynamic environment for complex reactions. Water dissolved minerals, forming a primordial soup rich in ions and molecules. Life might have originated in hydrothermal vents driven by chemical gradients. Zinc might not be the first element that springs to mind when we think about life, but it plays a crucial role in numerous biological processes. It's a vital component of many enzymes, those biological catalysts that speed up chemical reactions within living cells. These zinc-containing enzymes are involved in a wide range of cellular functions, from DNA replication and repair to protein synthesis. Zinc's importance for life goes beyond its role in enzymes. It's also involved in maintaining the structure of DNA and RNA. Zinc ions help stabilize the double helix structure of DNA. Furthermore, zinc plays a crucial role in cell signaling. Zinc ions act as signaling molecules, binding to specific proteins and triggering events within the cell. The findings of this research have far-reaching implications for astrobiology, the study of life in the universe. Unmelted planetesimals carrying volatiles suggest that the ingredients for life could be more common throughout the cosmos. If similar processes occurred in other star systems, many rocky planets in habitable zones could have received volatiles. This means the potential for life to emerge on other worlds could be higher than previously estimated. Zinc's crucial role in biological processes adds another layer to our search for life beyond Earth. As we gaze up at the night sky, we can't help but feel a sense of awe and wonder at the vastness of the universe. Billions of stars, each potentially orbited by planets, some perhaps similar to our own. The discovery that the key ingredients for life on Earth might have been delivered from space raises a tantalizing question. Could the building blocks of life be scattered throughout the cosmos, carried on the backs of celestial messengers? If the processes that led to the formation of our solar system are typical, then similar events have unfolded countless times across the universe. If this is true, then the universe might be teeming with life, a symphony of diversity played out on countless worlds across the vast expanse of space. The search for extraterrestrial life has captivated humanity for generations, fueling our imaginations and driving scientific inquiry. The discovery that life's building blocks might have come from space provides a new lens through which to view this profound quest. It encourages us to broaden our search criteria, looking beyond just Earth-like planets. Perhaps life could exist in environments we once thought too extreme, fueled by alternative energy sources. The icy moons of Jupiter and Saturn, with their subsurface oceans, are now considered prime candidates for hosting life. The search for life beyond Earth is no longer limited to looking for planets that mirror our own. It's about exploring the full spectrum of possibilities, embracing the unknown, and challenging our preconceived notions of what life could be.